Hydrogen bond is a weak intermolecular force of attraction. Some molecules are held by hydrogen bonds. It is a weak electrostatic force of attraction existing among the molecules of the same or different kinds. By the end of this lesson, the students will be able to define hydrogen bonding, relate the existence of the hydrogen bonding to the boiling point, describe the effect of hydrogen bonding on the physical properties of some substances, and differentiate between inter- and intramolecular hydrogen bonding. The table above shows the boiling points of the hydrides of group 14, group 15, group 16, and group 17. Click on the graph button to view. Click the group 14 button. The graph above shows the boiling points of the hydrides of elements of group 14 plotted against the period number. Click the group 15 button to plot a graph of the boiling points of the hydrides of elements of group 15. There appears to be a similar trend for the hydrides of group 15. Notice that the first member, ammonia, is not shown. Use the trend to estimate the boiling point of ammonia by clicking the extrapolate button. What is the actual boiling point of ammonia? Click the answer button to see the actual value. Now, click the Group 16 button and then the Group 17 button. Notice that a similar pattern appears where the boiling points of ammonia and hydrogen fluoride are higher than extrapolation of the graphs would suggest. What can you deduce from this? Water, liquid ammonia, and liquid hydrogen fluoride must have much stronger intermolecular forces than usual. Look at the Lewis structure of ammonia, water, hydrogen fluoride, and methane. Apart from the fact that they all contain hydrogen atoms, what two other features do ammonia, water, and hydrogen fluoride, but not methane, have in common? Answer: the hydrogen atoms in ammonia, NH3, water, H2O, and hydrogen fluoride, HF, are covalently bonded to a highly electronegative atom which has one or more lone pair of electrons. Hydrogen bonds are forces of attraction between a hydrogen atom, which is covalently bonded to a very highly electronegative atom, such as nitrogen, oxygen, and fluorine, and another atom that is also very highly electronegative. Hydrogen bonds are about 1/10 as strong as covalent bonds. Molecules which form intermolecular hydrogen bonds will also be attracted by van der Waals forces. Look at the molecule of hydrogen fluoride. What is the polarity of the hydrogen fluoride molecule? Drag delta positive and delta negative charges into positions over the molecule. Each hydrogen fluoride HF molecule can take part in 2 hydrogen bond formations, but forms an average of 1 hydrogen bond per molecule. Look at the molecule of water. Drag a second water molecule down towards this water molecule in such a way that a hydrogen bond can occur. Drag more water molecules to form the maximum number of hydrogen bond interactions that is possible with the first molecule. Each water molecule can form an average of 2 hydrogen bonds. Look at the ammonia molecule. In the molecule of ammonia, there are 3 hydrogen atoms and 1 lone pair of electrons. How many hydrogen bond formations can a molecule of ammonia form? Click Next to find out. Each ammonia molecule can form an average of 1 hydrogen bond. Hydrogen bonds are forces of attraction that are formed between a hydrogen atom, which is covalently bonded, to a very highly electronegative atom, such as nitrogen, oxygen, and fluorine, and another atom that is also very highly electronegative. Look at the table above. Click the Sort button to rearrange the boiling points in descending order. Why do you think the boiling point of ammonia is the lowest of the 3? Click the Sort button to rearrange the electronegativity difference of the various bonds in descending order to help you figure out the answer. Answer: NH bonds are least polar as nitrogen is less electronegative than oxygen and fluorine. Hydrogen bonding between ammonia molecules is therefore the weakest of the 3. Fluorine is more electronegative than oxygen, but the boiling point of water is higher than that of hydrogen fluoride. Click Next to view the hydrogen bonds in water and in liquid hydrogen fluoride. To form a hydrogen bond, we need a hydrogen atom and a lone pair of electrons. On an average, hydrogen fluoride can form only 1 hydrogen bond per molecule because it has only 1 hydrogen atom. Water, on the other hand, has 2 hydrogen atoms and 2 lone pairs. On an average, it can form 2 hydrogen bonds per molecule. Water can therefore form more hydrogen bonds than hydrogen fluoride. Hydrogen fluoride and ammonia form an average of 1 hydrogen bond per molecule. Water forms an average of 2 hydrogen bonds per molecule. The strength of the hydrogen bonds is affected by the average number of hydrogen bonds per molecule as well as the polarity of HX bonds, where X is nitrogen, oxygen, or fluorine. Hydrogen bonds can also be formed between atoms of the same molecule. Look at the molecule of 2-nitrophenol. Click the Charges button to display the delta plus and delta minus charges over the atoms in the molecule. Click the Bond button to see the formation of a hydrogen bond. The hydrogen atom is now not free to form hydrogen bonds with the other 2-nitrophenol molecules. 2-nitrophenol molecules are therefore held mainly by van der Waals forces. Now look at the molecule of 4-nitrophenol. 4-nitrophenol has a higher boiling point than 2-nitrophenol. Why is this so? The hydroxyl group in 4-nitrophenol is not close enough to the oxygen atoms of the nitro group to form hydrogen bonds with them. 4-nitrophenol is held by intermolecular hydrogen bonds. Intramolecular hydrogen bonds can be formed between atoms of the same molecule. Ethanol is miscible with water, but chloroethane is not. Chloroethane does not form hydrogen bonds with water. It is only slightly soluble. This is because ethanol can form hydrogen bonds with water molecules and is therefore soluble in water. The molar mass of ethanoic acid from measurements in the vapor phase is twice as large as expected. This is because ethanoic acid forms hydrogen-bonded diamonds as shown. Solid water, ice, is less dense than water. This is because each water molecule in ice is hydrogen-bonded to 4 other water molecules in a tetrahedral arrangement. This arrangement creates a very open structure where the molecules are less closely packed than in the liquid state. The presence of hydrogen bonds affects the boiling points and melting points of ammonia, water, and hydrogen fluoride, the solubility of ethanol in water, the molar mass of ethanoic acid in the vapor phase, and the density of ice.